You are not happy. That's okay. Because that was annoying. But please realize, that computation only served to draw the connection between where we were with confidence interval and where we are now with this newfound test statistic. That's all. That's all. The question is that far enough away from center to be believed significantly lower? Is it lower than average? How can you tell it's lower than average right now? It's negative. So you know it's lower. The question is it significantly lower? So this is where step 3 comes in. Step 3 is going to be to get that magical p-value. So let's shift forward. Step 3 is to take that z equals negative 1.85 and try to see if it is statistically significantly lower than 0. And we're not going to know that until we turn it into a p-value, which essentially is going to paint us the picture of a one-sided confidence interval. It's essentially going to paint us the picture of a one-sided confidence interval. So that's step 3. We've got our test statistic, step 2. And the reason I erased all the work we just did is because in a moment we're going to use technology and you will just get this for free. It will do that entire annoying computation I just struggled through up here, and it'll just vomit out that test statistic for you, which is what I care about. I care not about you arithmetically computing that thing. I care about you knowing if that's significant or not. So let's find out. Let's find out. Let's move this thing down. Where are we going to put that negative 1.85, friends? Where are we going to put it? Based off our discussion from yesterday. Step 3, p-value. Step, whoops. P-value. Where's it going to go? Where's it going to go? It's standard deviations, right? So where's it going to go?
To the left.
Good. On where? To the left of?
Average.
On an average. An average is? Well, yes. No, you got it. Mu or P. But in general, okay, 0. Beautiful. 0. Good. You're saying the correct thing. I'm looking for a more specific answer. You're giving me very general answers. I love the general answers. It means you're ready for the rest of the course. Where's negative 1.85? Somewhere over here, right? Negative 1.85. How are we going to measure if this is significant or not? Ashley?
Like turn it into like a raw score, right?
We could, although I don't want to because I want to use your normal program, which means I want to leave it standardized. I love that idea, by the way.
So I can use that and take the area. Was that a p-value?
You guys are both saying the same thing in 2 different ways. We need to find the area that lives with that thing on the bell curve I don't see yet. There's a bell curve, isn't there? Isn't there a bell curve?
Yeah.
Central limit theorem promises us there's a bell curve. Its highest point is right here.
Yeah.
The highest point is right here. Okay? This 1.85 is somewhere over here. But the thing is, I don't know if it's really high here or really low here. If it's really high here, in other words, if this curve is very, very wide, would this be unusual?
No.
Not at all. If it's very, very wide, that means the curve is very high, and that means the likelihood is very high, which means it belongs on this curve, which would mean our flu vaccine doesn't work. Nice connection. Exactly. If the curve is up here, that means this negative 1.85 is close enough to 0 to be like, it belongs on that curve. It's not far enough away to not be on that curve. But if the curve is very, very, very low right there, that would mean that this is extraordinarily short, which means the likelihood is very low, which means it doesn't belong on this curve. So our job right now, our job is to figure out this. That, my friends, is your p-value. That area right there is your p-value.
3%.
That's your p-value. And our job is to figure out what that is. And this is where the 243 kickback comes in. For a moment. Your TI has lots of built-in to do this for you automatically. But right now, before we go right to that TI built-in, I want to turn this into a 243 problem. Actually, I love what you said about converting it back to a raw score. But since we already changed it from the raw values down to a z-score, let's just leave it as a z-score. I love your idea. But it creates one less job for us. Oh, before I go any further, that 0 is definitely 0. And tying into what Ashley said, really, that essentially is 12%, isn't it?
Yeah.
That's what it stands for. It's a normalized 12%. This negative 1.85, if you think about it, is a normalized 10.1%. So that would be your raw scores. But let's just stick with the z-score since we already have them converted. Michael?
Now, if that's the average,
Go
I'm
ahead.
having trouble with the confidence, because if that's 12% at that point, isn't that our limit, or is that not our limit?
That's the equal to 12%, and I'm not using quote marks.
Okay, yeah.
Because there's plus or minus around that 12% that we can be within and still say we are 12%.
Okay.
We're close enough to 12%. So let me see if I can phrase this correctly. We're close enough to 12% to not think it's not 12%. So it might be like 11.9. That's not equal to 12, but it's close enough to assume that it's 12. It might be 12.3, which is not 12, but it's close enough to 12. Now, as you start getting way out here, now people are getting sicker than they should, right? Now folks are getting sicker than they should. But we're not worried about that. Where is our 95% confidence interval, friends? Where is it? It's this whole shebang right here.
Oh, I see.
That whole thing is our 95% confidence interval that's built around this right here. It's built around this. Our job is to see if this guy right here is in it or not. Actually, I take that back. I take that back. It might not go all the way to here. It might go all the way to here. I'm not exactly sure yet, am I? I have to know what this area is, don't I? In order to know where 95% stops. For example, if this area is 7%, if this area were 7%, wouldn't the interval come all the way over here? If it was 95% confidence? Let's see if we got, make sure we understand that. If this area is 7%, or something like 7%, 8%, 9%, wouldn't the 95% confidence interval come all the way in past this and keep going? Because if it's 95% confidence, and this is 7%, it must encroach, because you can't add 7 plus 95 and get 100. It's more than 100. But if this is something like 1%, wouldn't that mean the interval would stop somewhere down here and have extra space? So our job is to figure out what the hell area is. It's the normal. We'll use it one more time. We'll use it one more time here. For those of you that didn't have me in 243, don't worry. You won't need this. You won't need this. Or you can use your tables. If you guys had down it for 240, you probably use the normal tables from your the back of your textbook. You can use that as well. So for us, programs to the normal. Okay, is this a forwards or a backwards problem?
Forward.
Most definitely forwards, because you have a z-score. So we have a z-score. We're going area to the left. The right bound is that guy, negative 1.85. Yes, here it is. There's our area. Looks just like our picture. Hot damn! The area is 3.22. 3.22%. So, friends, knowing that, does our confidence interval encroach that area or stop before the area? I hear one vote very quiet for stop before. Do we have a second on stop before? We have a second?
Yeah.
All in favor?
Yeah.
Perhaps? So we have a vote for this. We have a vote for that is our 95% confidence interval. And I'm going to put that in quotes only because your textbook doesn't actually call it that. Why does that have to be correct? From just an area point of view, not a statistics point of view.
Because your value wasn't high?
Right. This is 3.22%. If that's a 95% confidence interval, there has to be space between the two to add up to 100. So you got 3 here, 95 there, 98.22. There's still about 1.8% of space in here. Does that make sense?
Yep.
What does that tell you?
The vaccine is working.
I have a vote for the vaccine appears to be working. You have a second on that? Carrie says yes. I second that. I second that. Who wants to explain why? Why? I agree, because now we're at step 4. And step 4 is the conclusion. And by the way, just so you know, step 4 being the conclusion, let's go ahead. This is what I'm often going to ask for conclusions. State a clear, concise, contextual, correct conclusion that a non-statistician can understand.
Oh my God.
Okay, I call it my 5 C's. Clear, concise, correct, contextual conclusion. From now until about mid next week, this is how your conclusions are going to come at you. I'm going to have you circle either appears or does not appear at first. Until you get the hang of how they sound. Gesundheit. Until you get the hang of how they sound, all you're going to have to do is circle one or the other in the actual statement of the conclusion. That's all you're going to have to do, is circle one or the other. Chris, go ahead.
Well, isn't it because it doesn't encroach, so that means...
Hold that thought, my friend. Just hold that thought, okay, if you don't mind.
Okay.
So here's the deal. there are many things you could say at this point that are all correct. I want to hear Kristen's first in a minute. But first of all, we had a vote for it appears the vaccine is working. Are we all okay with that?
Yep.
What I want to do now is I want to make sure why we believe that. And we don't believe that it's not working. Does that make sense? We want to throw away the idea that it's not working. Okay, so I'm going to mute this screen down again. I want to come back. I want to come back to this. Oh, Carrie, you're still writing that down? No, here you go. You ready? State a clear, concise, correct, contextual conclusion, and here's the biggie, that a non-statistician can understand. Imagine you're in your yard trimming the hedge between you and your neighbor's house, and your neighbor just said, I just read a report that if I eat more than 5 oranges a day, my toenails are going to fall out. Okay, and then you ask for data, and they give you the data because your neighbor's a non-statistician that collects data, or at least gives you the magazine that it came out of, or shares with you the link to the website that the report was founded in. And you, being clever statisticians, back check the article, find the raw data, and it comes up with a p-value of 2.8%. And you go back to your neighbor and go, you know what? You should believe that. You should believe that. And they go, why? And what are you going to say? Are you going to say reject the null hypothesis? You could say that. Would this be right here, my friends, a rejection of the null hypothesis?
Yes.
It sure is. What does the null hypothesis say?
Greater than or equal to
Right.
12%.
The null hypothesis says our data should fall within the 95% confidence interval that is equal to or greater than 12%, which means if we were to believe that, our data should have landed in this orange region over here. But it didn't, did it? It landed over here. So we reject the null hypothesis. And that's fine to say that, but not to your neighbor. Because your neighbor's not going to know what a null hypothesis is or why he or she should reject it. So why do we say the vaccine appears to be working? Use a double negative. Use a double negative to explain.
Well, it's not working.
Perfect. We basically have data that implies that it's not working. It's not working. It's not lowering. So if it's not lowering, it looks like it's actually lowering. It can't be this. This is defined as not lowering. Correct? That's what that means mathematically. No, sorry, you can't see that. I put that. That null hypothesis, that's lowering. That's not lowering. You just showed that this is most likely not true. Therefore, if this is most likely not true, that's most likely the supportable hypothesis, most likely true. Does that make sense? Are you guys buying that? That's why we circle over there in step 4, it appears that the vaccine is working to reduce flu rates. Essentially, you set up a contradiction, just like Jamie just verbalized for us. Perfectly said. It appears that the vaccine is working because there's no evidence to think it's not working. It landed in the correct place. So here's your one-sided confidence interval. A small p-value puts you outside of it. I want to make one small nod to old school statistics. This right here has a value. That's going to be the final endpoint of that 95% confidence interval. What number would go there? Can you use the normal to figure out what number that is? What number of standard deviations would put you right there?
1.
I love what I just heard 2, or -2 in that case. But that's for a 2-sided interval. That's when you have 2.5% on both sides. But we've taken that extra 2.5 from this side and put it over there, which actually moves the interval over. So it can't be -2. -2 would be over here, to the left of -1.8. So what is that number right there? Can we use the normal to find it?
Yeah.
Can we use the normal? I think so. Let's use the normal. I guess I lied to you. We're going to use the normal again here. So more probabilities. Is this forwards or backwards? I think it's easier to do it backwards. Why would it be easier to do it backwards? Because you know what percentage you're looking for. Here's the deal, right? Remember what I asked you? I said, what is the z-score? Oh crap, I don't know what the z-score is. In order for it to be a forwards problem, I have to know the z-score. But I don't. So I do know this is 95%. So let's use that. Let's go with a backwards problem. Shading to the right 95%, 0.95. Could you shade to the left 5%? Of course, exactly the same z-score, if you want to. All I'm going to do this time is I'm going to shade the entire, there's the confidence interval right there. Boom! Negative 1.64. That's the cutoff, friends. Don't memorize this value, please. Don't memorize this value. You don't have to memorize the value, because the p-value will tell you if you've exceeded it or not, or in this case, de-exceeded it, if that's a real word. I don't know if that's a real word. Exceeded. If you've exceeded the absolute value, let's say it that way, that's mathematically correct. You don't have to memorize this number. You don't have to memorize this number, because the p-value, the percentage, will tell you whether or not you went to one side of it or not. Go ahead, Carrie. Tell me.
I was just saying, could you just minus that?
This and this?
No, the 95 and the 3.2.
Oh, sure, and see if it's greater than 0. You can, but that takes just more work for us. Just look at the p-value itself. If it's less than 5%, who do you believe? If your p-value is less than 5%, Jamie, you look in the right place. You believe H1. You believe. If your p-value, this is kind of a nice mantra to repeat over and over again. If your p-value is less than 5%, you believe the research hypothesis. You believe H1. If it's not, you believe H0. There's no reason to not believe it. But if it's less than 5%, there's every reason not to believe it. Does that make sense? Ish? Now here's why I don't want you guys, I'm going to come back to this example in a minute. Here's why I don't want you guys getting all worked up about all that work we just did. I know it took us about half an hour to slug through all that mathematics and all this curve drawing and all. It's very, very, very nice. There is a TI shortcut that I want us to play with right now. Okay? Everybody kick out of your STEMnormal program. You're not going to need STEMnormal, and here's why. Go back to your stat test screen. Remember how we had one prop z int for single proportion confidence intervals? We now have one prop z test, which is the same thing, but it's hypothesis testing instead. So what I'm going to do is I'm going to erase this curve.
Number 5?
It is number 5. It was number 5 on mine, though, Chris. Everybody see it? Number 5 on mine?
Yeah.
So you got it?
Yeah, I just had a different question.
Please ask me that question.
So, if for it does not appear to be working, what should it have to be like?
We'll make up some data. We'll make up some data here in a moment, okay? What I want to do is I want to mess with the results of this. Oh, I love that. I love that, friend. I love that. Let's hold that thought, okay? Please hold that thought. Yeah, Joey wants to see what happens, what if we get one that does not work. So we'll see you momentarily, I promise. So let's just see how we can make sure we can run this particular test. Now, if you think back to what one prop z int looks like, it looked a lot like this. It had this and it had this. And then it had a confidence choice down here. There is some difference here between one prop z int and one prop z test. The difference first is this little p naught up here. That's a strange symbol. TI invented it. What they mean is put in the percentage that's in H naught. So put in 0.12. I have a series of steps in your homework assignment for this section that actually has all these outlined for you, so you don't have to memorize it right now. Plus, we'll do a whole bunch of them today and Thursday that'll make it hopefully become second nature to you. X and N are exactly what they should be, 101 out of 1,000. That's your sample. Here's your sample. So that's your assumed flu rate. Here's your sample data. Down here, can anybody figure out what this is? Anybody figure out what this is right here? This is whatever sign is in your research hypothesis. Either does not equals, less than, or greater than. Ours is less than. Ours is less than. So what we're trying to see is it the case that our sample data appears to imply that our population, or excuse me, that our flu vaccine using population is less than P naught, which is 12%. It's a very strange, convoluted way of putting things in, but this is how the TI gives it to us. Everybody seeing how the sign matches? This is why I make you write the hypotheses down. All you got to do is pull that sign and drop it in there, and you're good to go. You ready? Go ahead, Joey.
Wait, so we're plugging in H1?
You're putting in the sign from H1 down here, and you're putting in the value from H naught up here. And look for the indication. The little naught right there. That's the indication for the value from naught. And there's no good way. It says prop. P-R-O-P. That means little p, I guess. So is that fair? You'll get used to it, I promise. It's TIEs. It's TIEs, and I haven't gotten around to writing a program that makes it more Englishese than TIEs. So, value from H0, sign from H1, and your sample data. James, does that answer your question?
Yeah.
Okay, good, good. Let's draw it. I don't particularly like calculate, I like draw, because draw gives you the entire graph. Does that graph look familiar, friends? Does that graph look familiar to you? It does. It's the normal graph. I actually based the normal off the results of these output windows. I wanted it to look like this, so when you got here, it was like, oh, okay, I know what that means. One thing I don't like the fact this is a little p. That should be a big P, shouldn't it? That's a big P value. That pisses me off with a capital P. All right. But it means the same thing. It's 3.22%. Now, what it doesn't show you, and it doesn't have to show you, it doesn't show you that cutoff or 95% stops. But why don't you need to know that?
Because we already know that it's less than 5%.
You know that it's less than 5%, so you know it's outside the confidence interval. There's no need to know. What I'm just describing to you is what used to be called the classical method for doing these, where they would put the cutoff up and then you'd see which side it fell to. You know which side it falls to based on what just happened. You know it falls outside the confidence interval. So you know that it appears the vaccine's working. Is that fair? Karen, does that make sense? That was a good yawn. That's not like a good one.
No, I said let's do it again.
Oh, God, I'm thinking a number more times, yes. But before we go anywhere, could we be wrong? Could we be wrong with the results of this test?
Yes.
How? What kind of error could we have made with this test? I hear a vote for type 1. Do I have a second on the type 1 error? Oh, good, we're thinking about that. Let's think about this. Ashley votes for type 1 error. What is type 1? Look back at your notes, totally fine. Look back at your notes, friends. Could this be a type 1 error? What is a type 1 error? Think about what Ashley Parkhurst said about half an hour ago. It's related to what she said. You may have forgotten. I have not, because it was awesome. That's okay. I have it because it was awesome. Darla?
Say something changed, but it didn't.
That's beautiful. That's a false positive. This would be a potential false positive. Why is it a positive? Gesundheit. Why is it a positive test result again? Because we said something changed. Didn't we say something changed? It appears, Gesundheit, that the flu vaccine is working. Give it to Ashley. She's sneezing a lot. No, I'm kidding. It appears the flu vaccine is working. That's saying something changed. What's status quo? Let's go back over here. Status quo says we believe this. That would be a negative test result. Nothing's changed. But we said we believe this, which means we believe something has changed. We could be wrong. And what's the chance that we're wrong?
5%.
Always 5%, because we're testing at 95% confidence. The only reason is always, I know that this is 3.22% up here. I totally get that. But even if that came back at 3.82, wouldn't we still say the same thing? We'd still say it appears the vaccine's working. If it came back at 4.22%, wouldn't we say the same thing?
Yeah.
It appears the vaccine's working. If it came back at 4.99%, wouldn't we say the same thing? So in other words, the decision we're making based on this test is based around that number 5%. We're comparing everything to 5%. And that's why the chance of that type 1 error is always 5%. Regardless. Is that fair? Could we have made a type 2 error on this test? Could we have made a type 2? This is a bit of a tricky question. And it goes back to what Zoe said earlier today. I don't want to come back to that. Could we have made a type 2 error? It's a false, it would be a false negative. We couldn't have made it for this one, could we have?
Because then nothing changed.
Because we didn't say nothing changed. The only way you can make a false negative is if you get what kind of a p-value? A big one. A big one. So let's see one of those, shall we? Let's see a test that has data that results in a false negative. Is that okay? I had a request for more data sets. Michael, go ahead.
My concern is, where does 12 actually fall in this graph?
Great question. Great question over here. Where does 12 actually fall on this graph? Carrie Price, want to come and draw it in for us? If you don't mind, please. No, you don't have to, but I think you got it.
The average.
I was going to do the middle line.
Well,
Okay, then.
okay. Perfect. Where does 12% fall on this
Do you want
graph?
12 or do you want 0?
How about both? What the hell? 0 is implied to be there already, but that stands for 12. It goes, thank you, it's perfect. Golf clap, yes, golf clap. Very nice, very nice, very nice. It goes back to what Ashley said about 5 minutes ago. She said, why don't we convert back to raw scores? You can. That curve actually has 2 sets of scores on it. There's the standardized, the normal scores that's centered on 0, which means this bad boy out here is 1.85, or a z-score. This is the z-scale, if you will. But there's also a 12% here, of which ours is now 10.1%. That would be, if you will, your x-scale. The curve's shaped the same. The curve is shaped exactly the same, both ways. It's just that as soon as you create the test statistic, Michael, over here, please. This is a good question, very good question you just asked. Gesundheit. As soon as you do this, you lose the context of the problem. And that sounds like a bad thing, but it's actually a good thing. As soon as you subtract p hat minus p, that's a percentage, and you divide it by a standard error, which is also a percentage divided by percentage, there's no unit anymore. So now you're centered on 0, which is average. So by virtue of the mathematics of the units, you're back at 0, which stands for the 12% center, because that's what Rex was right here. But no matter what data you start with, they're always going to be centered on 0 right there. It might just take time to kind of let that wash over a process.
Yep.
But that's where it is, friend. Whatever that number is always going to be represented by that 0 that's right there.